Hello, welcome to Team 2's presentation of Thermodynamics Question 7 from the SmartWorks online homework. This presentation is by Hargun, Askar, and Dorisonia. Part 1 is to write a balanced equilibrium equation for the dissolution of NaI in water. Part 2 is a multiple choice question about why entropy change is greater for the dissolution of NaI compared to the dissolution of NaBr. Part 3 is to calculate the change in free energy if 1.4 moles of NaI are dissolved in water at 25 degrees Celsius. And part 4, what is the dissolution of 1 mole of NaBr at 298.15 Kelvin? Before we begin solving the problem, let's go over some essential terms and concepts that you will need to solve this problem. This question is about the dissolution of NaI in water. The dissolution of a substance specifically depends on its intermolecular forces. So for this problem, NaI is a salt dissolving in another nonpolar substance, water. The weaker the attraction between the sodium and the iodine, the easier it is for the salt to ionize in the water, or split up into individual ions. The intermolecular strength depends on mass, size, distance between nuclei, and polarity. For example, as the radius of an ion increases, distance between two atomic nuclei also increases, which leads to weaker IMFs, making it easier to ionize the compound. When predicting whether a reaction will favor the forward or reverse direction until equilibrium, you must look at 3 factors: enthalpy, entropy, and temperature. The enthalpy of a substance is equal to how much energy is stored in the substance. This is mostly influenced by the energy between the bonds within the substance. There are multiple ways to calculate enthalpy. In one method, you can look up the enthalpy of individual compounds in a table online and then subtract sum of the enthalpy of reactants from the sum of the enthalpy of the products. When we solve this problem later on, we calculate the enthalpy to be negative. A negative enthalpy indicates an exothermic reaction and release of heat. Typically, but not always, an exothermic reaction indicates spontaneity in the forwards direction. So, we calculate the enthalpy of the solution to be negative, but this can only be obtained after considering the enthalpy of solvent and enthalpy of mixing. Enthalpy of solvent is how much heat was gained or lost by the solvent, and likewise, enthalpy of mixing is how much energy was released or absorbed in the overall reaction. Negative enthalpy means the solution is losing energy. The solvent is also losing energy, but the energy is being absorbed by the surroundings in a net zero of energy. The second factor is entropy, which is disorder. We'll elaborate more on entropy in the upcoming slides in terms of Gibbs free energy. But entropy is a measure of disorder in a system. It can be defined in more than one way, but the simplest way of thinking about it is a measure of equal energy microstates that can exist at a certain point in time. The second law of thermodynamics actually elaborates on this and states how as time moves forwards, entropy of the universe must increase, never decrease or be negative. This refers to overall universal entropy. So even if in a reaction, a closed system reaction, the entropy of a system decreases, the overall entropy, looking at the big picture, increases in the universe.
So we'll start this off by talking about terminology. So dissociation is basically the breaking apart of a compound into smaller parts and then putting them all back together, but basically in a different way. Gibbs free energy change is a quantity that is associated with a chemical reaction that is used for work. Spontaneity is the reaction without any external energy, meaning it doesn't need any outside forces for it to occur. Entropy is a quantitative measure in thermodynamics of a disorder or randomness in a system and can be changed by many factors like temperature, volume, phase, mixing, and composition. Is the dissolution of either compound temperature dependent? So for this, I'd like to just think about the definition of what dissolution is. So basically, it's when a gas, liquid, or a solid is placed into a liquid or another solvent and becomes solutes, basically dissolved components. So I'd like to think about what it takes for it to completely be soluble. So does it need a lot of heat? Does it not need a lot of heat? Is it endo or exothermic? How do intramolecular forces account for the difference in entropy change? So for intramolecular forces, they basically hold substances together and are based on how weak or strong it is. And basically it determines the state of matter, like if it's a solid, liquid, or a gas. This means it plays a huge role in entropy change because entropy change is based on the randomness and the position. And each state has a different position, meaning that they'll experience change differently. So for example, like a liquid is said to be closely packed together, therefore it will experience entropy change differently from a solid. Does entropy of this system increase or decrease upon dissolving these compounds? Entropy usually increases when a liquid or a solid dissolves in a solvent. To start the solute, the solvent is completely separated from each other, and then after everything's placed back together, they become separately scattered. So this means that entropy increases. And then when entropy is decreasing, it usually involves gases that are dissolved in a liquid or a solid. Basically, there's more mixing involved, but the atom of the gas go from being completely separated to being closely packed together. Therefore, it decreases.
Solving the problem. Part 1. Varying the balance equation. We're dealing with the dissolution process. The ionic bonds are being broken within sodium iodide, yielding us a solvated cation and solvated anion. Part 2. Explaining the entropy change. Both salts are being dissolved into a sodium cation and their respective anion. When comparing sizes of any anions, iodide with its larger radius will have the weakest ion dipole network with water per Coulomb's law, allowing for a higher degree of disorder, which leads to a greater entropy. Answer choice C. To find change in free energy, we need to use Gibbs free energy equation and solve for delta G. We calculated the delta G value to be negative 29.6 kilojoules per mole. After we adjust for the number of moles, we get the answer of negative 11 kilojoules per 1 mole of sodium iodide. For solving the problem part 4, we need to find out if dissolution of sodium Br is a spontaneous process. In the previous parts, we calculated delta G to be negative, which means that the change in the free energy is negative, meaning that the process is indeed spontaneous. Conclusion. Solving the problem allowed us to practice several concepts in conjunction. They were solubility rules and sizes of atoms, Coulomb's law, which defined the relationship between ion dipole interaction between water and iodide, allowed us to conclude that weaker interactions lead to greater entropy. We also practiced utilizing the Gibbs free energy equation and adjusting it for moles. In the last part of the problem, we used the negative value of Gibbs free energy equation of change in the free energy, and which implied that the reaction in question was a spontaneous process.